So the applications for chapter 6 I tried to keep pretty straightforward. So I just chose proportions, and I chose 3 types of proportions. So the first type is going to be map distances. Now, this one that we're doing here could work for like conversions of money, it could work for kilometers driven per liters of gas, it could work with all kinds of things, but we're just going to do it for maps first. So for example, on a map, if the distance between Nelson and Vancouver is 7.25 centimeters, and the two cities are actually 659 kilometers apart, if on the same map, the distance between Nelson and Spokane is 2.63 centimeters, what's the actual distance? What's happening here is they're setting up a ratio. So a ratio of actual distance to measured distance. And then you're going to have 2 equal ratios that you can use to solve for an unknown. So what we're going to have, and it doesn't matter, but the 2 things are a measured distance compared to an actual distance. And it doesn't matter which one goes on top and which one goes on the bottom, but they will always give you one known proportion or one known ratio. So for this one, it says Nelson to Vancouver is a measured distance of 7.25 centimeters to give you an actual distance of 659 kilometers. On the same map, so proportionally speaking, the distance between Nelson and Spokane is 2.63 centimeters. So again, this is a measured distance. And you can sometimes look at the units to determine where it should go. And they want to know what is the actual distance. So we've set up a proportion where our unknown is in the denominator. How do we solve this? Well, we solve it like we do any other rational equation. What is the lowest common denominator? Well, it's 659 times x. So we're going to multiply both sides of the equation by 659x, and then we're going to eliminate or destroy. So we go 659 is gone, x is gone, and I'm left with 7.25x, I don't need the units anymore, is equal to 2.63 times 659. I don't need the 0.0, but I should keep it there. And then to solve for x, I'm going to divide both sides by 7.25. And I end up with x equals 2.63 times 659 divided by 7.25, which gives me 239.1 kilometers, being the actual distance. All right. So they're all kind of like this, so I only gave one example, but we're going to move on to the next type of proportion. The next one I chose is a nursing example. So I had a friend who was taking like an end of term nursing exam, and this is one of the things that she struggled with. So I was like, oh, this is something I can throw in here. So nurses use proportions to determine the amount of a drug to administer when the drug dose, or when the dose, is measured in milligrams, but the drug is packaged in a diluted form in milliliters. For example, to find the number of milliliters of fluid needed to administer 300 milligrams of a drug that comes packaged as 120 milligrams in 2 milliliters, you could use this proportion. You could say that your known ratio is that you have 120 milligrams in 2 milliliters. So if we want 200 milligrams, how many milliliters should we have? So it's a ratio of milligrams to milliliters. And then you set it up and then you could solve it. So this is the example that they give you in the textbook. I took it verbatim from your textbook questions, but these are the types of questions that you will be asked to solve. So for example, Dilantin 125 is a type of drug. It's available as 125 milligrams per 5 milliliters. If 300 milligrams is ordered, how much should the nurse administer to the patient? So what we're going to compare again is milligrams to milliliters. We have a known dosage of 125 milligrams per 5 milliliter. Then we want to set up a proportion where we don't know part of it. We know that we need 300 milligrams, so we're going to put the milligrams on top, and then we're going to solve for the amount of milliliters required. Again, this is a rational equation where my lowest common denominator is going to be 5x. Don't let the units get in your way. Sometimes I don't put them in my proportion, I just put them out here, but whatever works for you. So I'm going to multiply every single term in my equation by 5x, and then I'm going to simplify. 5 goes away, x goes away. And what you might end up noticing is that every single time you do this, there's this thing that happens, and some might call it cross multiplication. So there's this thing that plagues me in math all the time whenever we talk about fractions, which is that every time somebody talks about multiplication, they're like, cross multiply. I'm like, no, it's just multiply across. So when you're multiplying two fractions, you multiply across. This is actually where cross multiply comes from, is that when you have a ratio equal to another ratio, they call it cross multiply because it's almost like the denominators come up. But the reason why that's happening is because of this whole process. If you multiply both sides by 5x, the x goes away, you're left with the 5. Multiply by 5x, you get rid of the 5, you're left with the x. So this cross multiplying happens. But people do it in the wrong place and they don't know why they're doing it. So I'm like, just don't do it. Okay? So just multiply it or solve it like you would any rational equation. So then in my calculator, I'm going to plug in 300 times 5 divided by 125, and I would get 12 milliliters. So to get a 300 milligram dose, I would need to administer 12 milliliters of the fluid. Awesome. I have another one here. These ones can be kind of trickier, so I gave another example. So why don't you pause the video and give this one a go? But the process will be the same. We're going to set up milligrams to milliliters, or flipped, it doesn't matter. Then you're going to have a known dose. So furosemide, I don't know what that's used for, is available as 40 milligrams in 1 milliliter. So that's my known ratio, 40 milligrams in 1 milliliter. If you like the units, add them. If you don't, don't. I want 15 milligrams to be administered. I need to know how many milliliters of this furosemide, I'm probably saying that wrong, I need. So I know 15 milligrams. I want to know milliliters. To solve this, my lowest common denominator would just be 1x. So I'm going to multiply both sides by x. On the right-hand side, the x goes away. Boom, boom. And I would be left with 40x is equal to 15. So to solve for x, I'm going to divide both sides by 40, and I end up with x is equal to 15 divided by 40, which is, crazy small amount, 0.375 milliliters. I actually took these questions off of a nursing dosage website that was helping students prepare for a test. So I guess you can give 0.375 milliliters. So it'd be a tiny amount. Awesome. So go give those proportional questions a go.